So this is the 33rd session on rigid body kinematics. This is in continuation of the 32nd video. Okay. So in this I'll slightly discuss some more theoretical aspects of the last portion of 32nd video, and then I'll take a numerical problem to demonstrate the concepts and principles involved. Okay. So see in the 32nd video, I discussed, let's suppose this is the frame under consideration. There is some moving line, P1, P2 are two moving points. At some instant, separation between these 2 points is R. ER is a unit vector from P1 to P2. Suppose R is the separation between the 2 points at time t. Suppose the 2 points are always confined to move in the same plane as seen from frame F. Suppose at some instant the line P and P2 rotates at angular speed omega with respect to F, say in clockwise sense. Its angular acceleration is also beta in say anti-clockwise sense. Omega and beta are both anti-clockwise sense. Acceleration of P1 with respect to F is A1F. It makes an angle of phi 1 with the line. And acceleration of P2 with respect to F is A2F. It makes an angle of phi 2. Okay. And velocity of P1 with respect to frame F is V1F. It makes an angle of theta 1. V2F is the velocity of P2 with respect to frame F. It makes an angle of theta 2 with this line. Okay. So I discussed the results which I discussed in the previous video. I'll write it here. Slightly it has become clumsy here, but I hope you understand what is. So two results I got. V2F cos theta 2 minus V1F cos theta 1 is equal to dr by dt. V2F sin theta 2 minus V1F sin theta 1 is equal to r omega. And for acceleration also we obtain two results. A2F cos phi 2 minus A1F cos phi 1 is equal to A2F cos phi 2 minus A1F cos phi 1 is equal to dr d2r by dt2 minus omega square r. Okay, fine. So, and one more result I derived. A2F sin phi 2 minus A1F sin phi 1 is equal to r beta plus 2 into what I discussed was 2 into dr by dt into omega. So these are the four results which we derived. Okay, fine. See, just discuss one point regarding the second equation. This is the first equation, this is the second equation, this is the third equation, this is the fourth equation. Okay. Regarding this second and fourth equation, I'd like to say one thing. See, here omega is the angular speed of line joining P1 and P2, omega. This omega becomes V2F sin theta 2 minus V1F sin theta 1 by R. This is valid irrespective of whether R is constant or variable. This formula is valid irrespective of whether distance R between the two moving points P1 and P2 is constant or variable. This valid is always valid provided the 2 points are always confined to move in the same plane as seen from frame F. They are provided 2 points are confined to move in the same plane as seen from frame F. So this is always valid. Provided the 2 points P1 and P2 are confined in same plane as seen from F. irrespective of whether r is constant or variable. Irrespective of whether r is constant or dependent on time, or dependent 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 on time. So this formula is always valid. Irrespective of whether r is constant or changes with time, this formula is valid. Irrespective of whether the 2 points always confined to move in the, irrespective of whether the distance between the two moving points is constant or variable, this is always valid. Okay, fine. Now regarding this equation, you see this term which you can recognize, this is just the relative normal acceleration between P1 and P2. This left hand side of this equation, left hand side of this fourth equation, this quantity is the relative normal acceleration by separation. This quantity is relative normal acceleration. So in this case, we must note one thing, that if suppose r is constant, distance between two moving points is constant, then we know that dr by dt becomes 0 from the rule of calculus. So this term goes away. In that case, beta becomes what? Beta becomes a2f sine phi 2 minus a1f sine phi 1 by r, where beta is the angular acceleration of line joining the points P1 and P2. So this is equal to relative normal acceleration by separation. Relative normal acceleration by separation. Alright. So this term is the relative normal acceleration by separation. This beta. Beta is equal to relative normal acceleration by separation. So this formula is valid only when r is constant. Whereas this is valid irrespective of whether r is constant or variable. R is varying with time or not varying with time, this formula is always valid. Only one condition is necessary. The 2 points P1 and P2 are always confined to move in the same plane as seen from frame F. But this formula for beta, this is valid only when the separation between the 2 points is constant. Okay, and the 2 points are always confined to move in the same plane. But if r is not constant, if r is variable, then this term also remains. R is not constant, then our formula is not valid. This formula is for beta is not valid because this term also comes. Okay, so if r is not constant, then our formula is not, this formula is not valid. Okay, fine. So this point you must note down very clearly. Okay, so this point I have cleared. So this is always valid, but this is valid only when r is constant. Otherwise, it's not valid. Fine. All right. One thing is there, suppose r is variable but omega is 0, then again this formula becomes valid. But we are taking the case when omega is non-zero, that we are assuming. That this formula is valid only when r is constant. Separation r between the two moving points P1 and P2 does not change with time. Then only this formula for beta is going to be valid. Otherwise this formula for beta is not going to be valid. Okay, so this point I have cleared. Alright. Now I love this one, alright. So I'll take a problem to demonstrate this concept involved. Okay. This type of problem was considered in detail in the chapter on the videos on relative velocity. If you go to those videos, then also you'll get it. Okay. There are playlists for relative velocity also. Playlists are there. So if you go to those playlists, you'll get all those things. Okay, if you search there. So I'll write down the question based on this concept. P1, P2 and P3 are the three moving points which are initially situated at the of an equilateral triangle of side length L. These 3 points begin to move with same constant speed v, such that, st meaning such that, the velocity of P1 is directed towards P2 and that of P2 is directed towards P3 and that of P3. So I love this one, okay? And that of P3 is directed towards P1. Okay. Now we have to find two things. Find first the magnitude of acceleration of any of the 3 points of the acceleration, the magnitude of the acceleration of these 3 points at an instant when the separation between the points becomes r. R. And second, radius of curvature of the path of any of these points in terms of r. And third point is this. Value of acceleration and radius when sub case A r is equal to L and B r equal to L by 2. Okay, fine. This is the question. I love this one. Okay. I love this one. Okay. So now I draw the diagram first. This is the initial diagram, okay? This is the diagram at time 0. P1, P2, P3 are 3 points. L is the separation between the 3 points at any instant, initial instant. Now, P1 begins to move, its velocity is directed towards P2, that of P2 is directed towards P3, that of P3 is directed towards P1. Okay. Now what happens? P1 begins to move. P1 comes here. So P2 comes somewhere here. P3 comes here, then P2 comes somewhere here. Now again P1 chases this. P1 comes here. P2 comes here. P2 comes here, and so on. So path of P1 will be something like this. Path of P2 will be something like this. Path of P3 will be something like this. Okay. Now first observation, what is the first observation? First observation is that at any instant of time, these 3 points form an equilateral triangle. Okay. So suppose let us assume that at some stage of the process, some instant t after beginning of motion, the situation is something like this. This was the original triangle. This was P1, P2, P3 here at time 0. And at some instant t, P1 has come here, P2 has come here, P3 has come here. Okay, like this, see. So this is the separation between the points at t time. Okay, P1 is here, P2 is here, P3 is here. Alright. Now see, at this instant, P1 is moving at a speed v towards P2. P2 is moving at a same speed v towards P3. And P3 is moving at same speed v towards P1. All these angles are 90 degrees, 60 degrees, 60 degrees, 60 degrees, equilateral triangle by geometry. Okay. Now see, P1 is moving in this direction. Let us consider any one of there are 3 pairs, P1, P2, P2, P3, P1, P3. Let us consider any one pair. Suppose we consider the pair P1, P2. Alright. Now see, P1 is velocity is in this direction. Path of P1 is something like this. Now we know that for a moving point, acceleration of point is a sum of tangential acceleration and normal acceleration. And we also know that tangential acceleration is the derivative of speed of the point. But in this case, speed of all the 3 points are constant. V is constant. So dv by dt becomes 0 for all the 3 points. So for any point P1, suppose its tangential acceleration is 0. Similarly, tangential acceleration of P2 is also 0. Tangential acceleration of P3 is always also 0. So that is the first observation. So AT1 is equal to AT2 is equal to AT3 is equal to 0. They are all zeros because speeds of all the 3 moving points are constant, and tangential acceleration of moving point is the time derivative of its speed. Since speed is constant, so all the tangential accelerations of the 3 points vanish. Okay, all the tangential accelerations of the 3 points vanish. So they are all 0. Alright, fine. Now we know An is the normal acceleration of moving point, that is v square by rho, where rho is the radius of curvature and v is the speed of the moving point at some arbitrary instant. And the direction of En hat is along the inward normal. Now see, P1 is moving something like this. Subsequently it will go something inside. For example, P1 is here. After some time P will go move something like this. Path of this will be something like this. So its En will be in inward normal this side, En1. And tangent is this side, Et1. Okay. So acceleration of P1 in tangential direction is 0. Its only acceleration is in this direction. Let's call it say A1. Similarly, acceleration of P2 is only along, because P2 will move something like this. So its normal acceleration will be something like this, A2. And P3 will move something like this. Its normal acceleration is something like this, A3. Let's call it A11, AN2, AN3. By symmetry, all these 3 normal accelerations will have same magnitude. AN1 is equal to AN2 is equal to AN3. They are all equal. Is equal to AN sec. Alright, fine. Now I have this one, okay? Now see, let us consider the line P1, P2. Okay, this is the line P1, P2 at some instant. Okay, P1 and P2. So normal acceleration of P1 is in this direction, A1, which is right angle to this line, and normal acceleration of P2 is in this direction, A2. This angle is 60 degree, and okay, fine, all right. Now see, this angle is 90 degree. All right, this distance is r. All right. Now I apply the formula which I discussed in the beginning of this class session video. I wrote a formula you should remember: a2f cos phi 2 minus a1f cos phi 1 is equal to d2r by dt2 minus omega square r. Okay. Okay. Now see this. We apply this formula to this line P1, P2. Now see, it's something like this. We apply this formula here. Okay. So in this formula, phi 1 is the angle between the acceleration of P1 and line P1, P2. Now since tangential acceleration of all the 3 points are 0, so this term goes away, only this remains. So this term itself is the total acceleration of P1, P. So acceleration of P1 is A1 in this direction, P2 is in this direction, and P3 also it's in this direction. Okay, I am only considering the pair P1, P2. Fine, all right. Now see, A1, phi 1 is how much in this case? Phi 1 is 90 degree. What about phi 2? Phi 2 is, see, in this direction, see, in this direction, this one. Phi 2 is this angle. This angle is phi 2. Alright, this angle is phi 2. So now what do we write here? A2f, just the acceleration of P2. A2f, F is ground frame. Phi 2 is how much? See, this is 90, this is 60, this angle is what? 30 degree. So this becomes, phi 2 becomes 150 degree. A2 cos 150 degree minus A1f. A1f is acceleration of P1, A1. Phi 1 is how much? 90 degree. Cos 90 degree becomes d2r by dt2 minus omega square r. Okay, fine. Now see, what I do, you consider this diagram again. P1 is moving at a speed v like this, P2 is moving at a speed v like this. Now what is dr by dt? dr by dt is the rate at which r changes with time. That is dr by dt. Rate at which r changes with time. That is dr by dt. So that is equal to rate of increase of r minus rate of decrease of r. Rate of increase of r minus rate of decrease of r. Now see, this rate of increase or decrease of r is decided only by the components of velocity along the line P1, P2. Now this v is this direction, its component along this line is v cos 60 in this direction, and v is also along this direction. So v cos 60 and v both will tend to decrease r. None of them will try to increase r. So rate of increase of r becomes 0. Minus rate of decrease of r becomes what? V in this way and v plus v cos 60 in this way. So v plus v cos 60 and v by 2 minus 3v by 2, that is a constant quantity because speed v is constant. So dr by dt is constant. This means d by dt of dr by dt becomes 0. That meaning d2r by dt2 becomes 0. So this term also goes away here. You can see this term will go away. Fine. Alright. Now I rub this one. Alright. So this term goes away and this term also goes away. So we are left only with this term, that's all. A2 cos 150 degree, this term goes away, cos 90 degree 0. This also becomes 0. So this is just equal to minus omega square r. A2 cos 150 degree minus root 3 by 2 minus omega square r. Now what is omega? Omega is the angular speed of line P1 P2 at time t. Now the points P1 P2 are always confined to move in same plane as seen from ground frame, which is the F frame. So omega becomes relative normal speed by separation, as we have been discussing in the first video on rigid body, second video on rigid body kinematics, theory part, and then subsequent numericals were there. Okay, you go to that video in the playlist, you'll get it. So omega is equal to relative normal speed by separation. Relative normal speed by separation, that is omega. Alright. Now what is the normal speed? See, V is along this line, P1 P2 itself. Component of V normal to P1 P2 is 0. So normal speed of P1 is 0. Component of normal speed of P2 is what? Component of V normal to this line. Now V makes an angle of 60 degree with this line. So component of this velocity normal to this line P1 P2 is V sin 60 degree. So relative normal speed by separation. So relative normal speed by separation becomes V sin 60, V root 3 by 2 minus 0. V is along the line P1 P2. Component of V normal to P1 P2 becomes 0 by separation R. So this becomes V root 3 by 2R. This is omega. Now this omega I substitute here. Minus minus goes away. A2 root 3. A2 root 3 by 2 is equal to omega square. Omega square becomes 3V square by 4R square into R. Alright. Now this I write it, okay? Now what do we get? So from this we see acceleration of P2 at some instant is 3V square by 2 root 3R, okay? And this is also the magnitude of acceleration of P1 and P3. This is equal to A say. This is therefore the required answer, okay? So A1 is equal to A2 is equal to A3 equal to how much? 3V square by 2 root 3R. 3V square by 2 root 3R. This can be simplified still further. So root 3 goes away. V square root 3 by 2R. That is equal to A1 is equal to A2 is equal to A3 equal to A say. This is therefore the answer to the first part of the question. Okay, fine. Now we have been, actually this I'll rub now this one. Okay. We have also been asked to find the radius of curvature of the path of these 3 points at this instant. So let rho be the required radius of curvature. That will again be same for all the 3 points by symmetry. So this means A1 is equal to A2 is equal to A3 is equal to V square by rho. So equate this to this. V square by rho becomes V square root 3 by 2R. Okay. V square goes away. R becomes 2R by root 3. Okay, fine. R becomes how much? V square by rho equal to this much. So V square by rho becomes 2R by root 3. So this is therefore the required answer to part 2 of the question. Now we are given 2 specific values of R. R equal to L, R equal to L by 2. So when R equal to L implies A1 is equal to A2 is equal to A3 is equal to how much? How much does it become? We replace R by L. It becomes 3 V square root 3 by 2L. First answer. And when R is equal to L by 2 implies A1 is equal to A2 is equal to A3 is equal to, this becomes 2 times L by 2. So this becomes V square root 3 by L. This is therefore the required answer. Okay. Now I'll work this one, fine. And rho also we have to find. So when R is equal to L, implies rho is equal to 2L by root 3, one answer. And second, when R is equal to L by 2, implying radius of curvature rho becomes 2 times L by 2 by root 3. That becomes L by root 3, which is therefore the required answer. Okay. So rho becomes how much? L by root 3. And in this case, rho becomes how much? 2L by root 3. Okay. So this problem has been fully discussed. Till here we have discussed, till here we have finished the third chapter on rigid body kinematics, that is the acceleration point of view. Now we have to take up the last chapter on rigid body kinematics, that is on instantaneous center of rotation. Okay, chapter on instantaneous center of rotation. So this I close it here, alright. So you go through it properly, if you understand it, you don't have to go anywhere else, this is more than sufficient. You take up any problem from any source, I am sure you are able to solve most of them. In case you have some difficulty, put those questions in comment box, I will answer it. Okay, fine. And all the playlists I will made. If you go to the playlist of rigid body kinematics, relative velocity, you will get all those videos which are there. Okay, you can easily scan, search those videos. Okay, fine. So I close it here already.